So with quadratic functions, there are three forms we've talked about before. There's a standard form.
We can't see your screen.
Of course not, sorry. My fault. Just staring at my huge head instead. Yeah, okay. So there's standard form quadratics, and standard form was ax squared plus bx plus c, and we'll say f of x equals. After standard form quadratics, we've talked about factored form. Which was a times x minus p x minus q. We'll say f of x equals. And factored form was important because that's the also like intercept form is what we could call it as well. It tells us where the x-intercepts are. And standard form, remember, tells us the y-intercept specifically. That's why we like standard form. And then the last form, vertex form, just tells us the vertex. And vertex form was a times x minus h squared plus k. All right. H comma k is the vertex. X equals h is the axis of symmetry. And in this one, to find the axis of symmetry, you could say x equals p minus q divided by 2 is the axis of symmetry. And in standard form, x equals negative b over 2a is the axis of symmetry. So we should be able to find the axis of symmetry in all the forms. And once you have that axis of symmetry, you can plug in the x value and you can solve for the y value. So it's nice once we have that axis of symmetry figured out. Okay, those are the three big things with the three big forms and the ways to find axis of symmetry for each of those forms. Okay. Your textbook might write it a little differently. They might write this as x sub 1 plus x sub 2 over 2. It's all the same thing to find the axis of symmetry. But it's just how your textbook might have it written instead of the way I've written it. I've just used P and Q over the years, so it's the same thing. All right, so that covers the three forms of quadratics, how to find the axis of symmetry for each one, and then to find the vertex, take that x value and plug in for y. All right, if you're looking for the vertex of each one. Okay, also with quadratic functions, we might need to know the quadratic formula. Which was negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And that's what the quadratic formula looks like. You can use that to find x-intercepts if you need to. All right, intercept form. But because we have our graphing calculators available, we have Desmos available, you can just graph it and look for approximate answers on the graph. If I ask you to find exact answers, then I'd expect you to find exact answers. Let me look at the test real quick. Let's see. Yeah, on the test, I don't think I asked you to find any exact answers, so I think you're going to be okay there. Okay. All right. Other things you'll need to know for quadratics. Let's see. How about writing an equation? So if I gave you a graph, let's go ahead and do an example. And we'll just say 1, 2, 3, 4, 5, 6, something like that. And then 1, 2, 3, 4, 5. All right, we'll say something like that for our graph. And now, if I were to ask you guys to write an equation for this graph. All right, we've done this before. I can't remember if we did an exact example in class or not. But it is funny because there are some, I think we might have done some homework problems that were like this. So you would have seen it on the assignments then. But for this particular problem, if I were to go ahead and plot a point here, let's say it's right there, and then sketch a graph, like something like that. And I would say, go ahead and write an equation for this graph. This is where the forms come in handy. First, I'd want to look at the intercepts and say, can I identify exact x-intercepts? And in this case, not really. It's between 2 and 3 and between 5 and 6. Next, I'd want to look at the axis of symmetry and the vertex. And right here, it looks like the vertex is 4, 5. So if I were to write this equation, I could say f of x equals a times x minus 4 squared plus 5. All right. And then I would just need one other point on the graph in order to solve for a. So like write an equation, and I'll say given, we'll say 3, 2 is a point on the graph. Sorry, I didn't have a good example worked up for us beforehand. So there's 3, 2. So what I would do then is I would plug in 3, 2, and it's going to help me solve for this a value, and then I would have my equation written for this graph. So I'd say 2 equals a times 3 minus 4 squared plus 5. And now I'm just simply solving for a. Subtract 5 from both sides. -3 equals a. So that would be my a value for this, which makes sense. The parabola is opening down, so it should have a negative a value. All right, so that does make sense there. And now I can go ahead and say, okay, f of x equals -3 times x minus 4 squared plus 5. That's how I would do something from like a graph, which I think IB might ask you something like that on a test. Here's a line. You have 2 points that you can identify. So go ahead and write the equation. Typically what I want is I either want vertex form or I want factored form. So if I can identify the x-intercepts, I can do factored form. If I can identify another point on the graph, I want to use that. Usually the y-intercept's a good one. On this graph, I didn't really give you guys a good y-intercept because it's going down too fast. The y-intercept would be way off the graph. It's going to happen eventually, but I would be really far away from it. Let's see. Turns out the y-intercept of this problem is 0, comma, negative 43. So not a great example for a y-intercept problem. But you would just use those 2 points to help you find the a value. If you were doing this in factored form, I would use the 2 x-intercepts, x minus p, x minus q, and then again use another point to solve for the a value. Okay, and then after I've got it written like this, I could technically put this in standard form if I wanted to. Right now it's in vertex form. And then I can put that into standard form by distributing first by multiplying this whole thing out, x squared minus 8x plus 16, and then multiplying by negative 3, negative 3x squared plus 24x minus 48.
Wait, did you FOIL the x minus 4?
Yes, I did. Sorry, I foiled it in my head. And then the last part would be to add the 5. And like I said, I looked on the graph and I saw the minus 43 on the graph because I just put it into Desmos. And then that verifies that I have the correct equation here because I have a minus 43 there at the end. So that means I did my foiling and everything correctly. But that's what this equation would look like in standard form. All right. But just showing you real quick, like we should be able to write an equation from a graph. And then after that, if we need to, we should be able to solve for the a value, and then there's our equation. Okay. So that's just an example of one thing we could do with quadratics. Another example would be from the graded assignment yesterday when I asked you to go ahead and write an equation from the word problem and then graph it, find the maximum value, all right, those types of things. Okay. We talked about cubic functions as well yesterday. Ax cubed plus bx squared, not yesterday, but on this unit. So a cubic function is going to be of this form.
Wait, what did you get for the factor or the standard form?
For standard form? Oh, sorry. I ended up with negative 3x squared plus 24x minus 43.
Okay, good. Thanks.
Okay. And now for cubic functions, we should have ax cubed plus bx squared. Let's see. Plus cx plus d equals f of x. And then, of course, we always want to say a does not equal 0, and that's just because otherwise it'd be a quadratic function. And then the way your book writes it is a, b, c, and d are all elements of real numbers, which is always true. That's the same with quadratics as well. All right. Some things to remember about cubic functions is we need to be able to identify local maximum and minimum values. So if I give you a cubic function, can you graph it, identify local maximum and minimum values? Okay. And it's important to remember when we looked at them and we did that warm up the other day, we say not all cubic functions, I think we did this on Monday, not all cubic functions have a maximum or minimum. We remember that some of them, we just saw them slow down and then speed back up again. So we saw that on some of them. Okay. And then another thing with cubic functions Cubic functions have 1, 2, or 3 roots.
Wait, how do they not have a maximum or minimum?
That was like if I were to graph something just like y equals x cubed, it's gonna slow down and then cross the x-axis and then speed up again. So it didn't really have any maximum or minimum values. It just kind of kept moving through. So that's what I mean. I guess the local maximum or local minimum values, right? That's how they would not have a maximum or minimum. Which we saw that when we did the warm up on Wednesday, or not on Wednesday, on Monday. We did that warm up that had a bunch of different problems like that. Okay. So that's what we can expect for cubic functions. You have 1, 2, or 3 roots. If I were to do an example of a cubic function, let's see. We would see a cubic function that maybe looks something like this. That's an example of one that has no maximums or minimums. No local maximum or min values. All right, and that's possible to see one like that. Okay, the other thing we might see is something that looks like this. All right, and this one has 3 roots or 3 zeros. We might call it roots, we might call it the zeros. This one has 1 0 or 1 root, but it's a multiplicity of 3. We kind of talked about that a little bit. And then an example where you might see 2 roots is if you see something that looks like this, where it goes up, comes down, touches the x-axis, and then goes back up. That would just be 2 roots right there. But this one has a multiplicity of 2. That's one of the things we talked about with cubic functions. All right, was just, can you sketch it? Can you identify those local maximum, local minimum values on your graph? All right, do you know how to do that? The other thing we talked about was the vertical line test and the horizontal line test. Okay. Oh, I'm out of room here. So cubic functions, vertical line test, and horizontal line test. To prove it's a one-to-one function. All right, one thing that we did not see on our graded assignment yesterday, but I said if we don't see it on the graded assignment, it's probably likely we'll see it on the test. We need to prove this is a one-to-one function, and if it is a one-to-one function, find its inverse. Okay. I'm going to cross off the power functions here. Or we'll write as f negative 1 of x. All right, so if it is one-to-one, find its inverse. All right. So that's the idea with cubic functions. So those are the 2 big things we talked about. Identify local maximum and minimum values. Maybe it doesn't have any. And then can you prove it's one-to-one and find its inverse? Those are the big things with cubic functions we talked about. With quadratic functions, I have a higher expectation that you can manipulate them and use them. Like that's something we've covered last year in AA math. That's something we covered in AGS2 a few years ago. All right, the cubic functions we haven't done as much manipulating with, but we should still be able to identify local maxes and mins. All right, and then the last part that we talked about in this unit was power functions. And really the only thing we talked about with power functions was direct variation and inverse variation. So if I gave you a problem where it said these two things vary directly, then you're going to do multiplication. These two things vary inversely, then you're going to do division. And if it's a real world situation, it should be pretty intuitive. So if I'm talking about like the number of cloudy days versus the amount of rainfall, that's probably going to be a direct variation, right? Like one of them leads to the other. All right, versus inverse variation would be like the opposite, right? The number of sunny days versus the amount of snowfall. Oh, well, it's like, well, there were a lot of sunny days, so there were fewer days with snowfall this year. That would be like an inverse relationship. All right. So that's the idea for power functions. We talked about direct variation versus inverse variation. On your review, I tried to include some practice problems here. So problem 10, for example, is like what we just did, an example of writing an equation from the graph. Problem number 8 is one of those open cylinder problems where we have to do a show that. So being able to prove one thing from another. All right. And then there's a direct variation problem right there with number 13. Okay, and then I have some actual IB questions. So these are the problem 17, 19, and 20 are old IB questions that you could actually see on a test. And these are all from your textbook, so they should all be in the back of the book to answer as well. And I think this is pretty much everything that's going to be covered on your test. We already did an optimization problem, so I wouldn't expect a big optimization problem on the test tomorrow. But I would expect something with direct variation, inverse variation. I'd expect finding one inverse algebraically for a cubic function. And I would expect being able to write an equation for a quadratic function. Stuff like that is what I'd expect for the test tomorrow. All right. Wow, we